Hello, welcome to section 3.5, Implicit Differentiation. This section goes over a method of differentiating an equation that's not necessarily expressed where y is a function of x. That's called an implicit equation. So we're going to be using the chain rule in this method, and we're also going to be using this method, deriving the derivatives of the inverse trig functions. So you want to remember or review your inverse trig functions. We can solve for y in this equation, and we know that this is a function. Its graph is a parabola. In this equation, we cannot solve for y as a single function of x. This is a circle, the unit circle. And when we solve for y, we actually have two functions, the upper half of the circle and the lower half of the circle. And we can't explicitly solve for y as a single function of x. So we can still get the derivative of an equation like this, y dy dx, so the derivative of y with respect to x, even though we can't solve for y necessarily. So that process is called implicit differentiation, and we don't need to solve for like y1 and y2 in this case for this equation. We're not going to need to solve for that. We can use implicit differentiation and find the derivative of y with respect to x. So implicit differentiation is when you differentiate an equation term by term with respect to x, and you treat any instances of y as a composite function where the inside function is this generic unknown function that makes the equation true. So for example, for x squared plus y squared equals 1, to differentiate with respect to x term by term, so the derivative of x squared would be 2x. Y squared I'm going to treat as a composite function where the outside is the power function raised to the second, right? And the inside is my unknown generic function y. So using the chain rule, the derivative is 2y, that's the derivative of the outside, times the derivative of the inside is dy dx. And then the derivative of this constant term 1 is just 0. And then I'm going to solve for dy dx, and my expression is minus x over y. So notice that I don't have an explicit formula for dy dx in terms of just x. Y shows up in there. I don't know what y is necessarily, but I do know I can express the derivative of y with respect to x in terms of x and y with this expression. So it's a little bit abstract right now because you're dealing with this unknown function. At first you approach it just learning the process of differentiating term by term. It kind of organically sinks into your brain as you go along that yeah, I'm treating this y as some function that works, even though I don't know what the explicit formula for y is. So 3 things to note with the result we just got. So we were treating that y squared term as a composite function, and so when I take the derivative of the outside is 2y to the first. And remember you with the chain rule you evaluate the outside function at the inside function, so that's why it's 2y. And then you're always going to have this dy dx multiplied by that the derivative of that outside function. So another thing to notice is we didn't use, even though in this case we could solve for 2 functions, y1 and y2, that solved this equation, we didn't use them at all. We could go back and solve this equation for y1 and y2, and then take the derivative of each of those, and the function, the formula we get for each derivative would turn out to work for all the points, just like this one does. But sometimes we don't know how to solve algebraically for y. Like if this had been x cubed and y cubed, or x to the sixth and y to the sixth, we don't know how to solve those, with our skill set. So this is actually sometimes necessary without having to solve for y, or being able to solve for y. So let's look at an example, another example. So this time I have the square root of x minus the square root of y equals 1. So I'm going to differentiate term by term. So I differentiate this term as usual. It's 1/2 x to the minus 1/2. And then this term that includes y, I'm going to treat as a composite function and use the chain rule. My outside function is that power function with the exponent 1/2. And my inside function is y of x. So I use the power, I find the derivative of the power function, and this is this factor, evaluated at the inside function, times dy dx, which is the derivative of the inside function, and then differentiating that constant term is 0. And we want to solve for dy dx. Ultimately, that's what you want to do, because a lot of the homework problems will either say find the derivative or find the equation of the tangent line at this particular point, and you need to solve for the derivative. So solving for dy dx, I get the square root of y over x.